So we're now going to turn our attention to situations where energy is sometimes lost in the sense that we can't use it anymore. Not that energy is ever lost completely, it goes somewhere. And we're going to call that lost energy dissipated energy, or sometimes I'll call it thermal energy because it pretty much always goes into heating up the surroundings. Let's look at those ideas a little more in detail here. So far we've been dealing with these three types of energy right here that are collectively known as mechanical energy. And in all of our equations, these were basically the only options, and energy could transfer back and forth between these types of energy. But we always ended up with the same amount that we started with. We could always bounce just as high off the trampoline as we started, and all of these fun things. But in reality, there's always friction or air resistance or some type of retarding forces involved, and these cause heat to be created. All you need to do is rub your hands together a little bit to realize that you're creating heat. And when heat is created, some of that energy is no longer available to do work. You can't use it anymore in a mechanical sense, at least not easily. When we get to thermodynamics, we'll see how you can recover some of it, but usually it's a very small portion, and you need a certain type of system set up to be able to do that. It is important to note that even though we say, oh, how much energy was lost, we don't mean how much energy was destroyed. We mean how much was transferred somewhere else. Total energy in every situation is always conserved. It just goes other places where we can't use it. And we can look at our good friend perpetually skating back and forth here at the skate park. So in reality, a person not moving their knees at all could never just keep going back and forth like this. I mean, imagine just throwing a skateboard down on a ramp. It's not just going to go back and forth forever. We call those perpetual motion machines, and that phrase is used to denote something that's impossible, right? So to make things more realistic, we can go here and we can turn some friction on. So we're going to adjust the coefficient of friction. You'll notice over here there's no thermal energy to begin with, just kinetic and potential like we saw the last time we looked at this. So if I add a little bit of friction, now we're going to get some heat. And that's going to cause what we normally see in the real world, which is a person slowing down, and eventually they will stop. Now, where does that heat go, or where is it created? Well, wherever there's friction. So the wheels and the ramp will each heat up a little bit. The axles will heat up a little bit. Even the air resistance of the skater pushing against the air will cause the air molecules to move a bit, and that is what temperature is movement of particles. So all of those things heat up ever so slightly. It's not like you would be able to easily measure that in some situations. In others, you surely can. Just using a drill bit, if you touch it, be careful, don't do that right after you use it, but a drill bit warms up, so you can definitely feel things heating up due to friction. But a lot of times, if you just slide a book across the desk, you put your hand on the desk, it's not that warm, but it did heat up ever so slightly. Alright, back to our PowerPoint here. So as far as problem solving, we have a couple of different approaches. The first that I'm going to show you is just using conservation of energy. So if we have something like a child going down a slide, stick child on the stick slide, and if we say that the child started 3 meters from the bottom of the slide, so here they've already gone down a little bit, and when they reach the bottom of the slide, they have a velocity of 5 meters per second, and let's say we know the mass of the child is 50 kilograms. In this situation, if there were no friction, the child would be going faster than that at the bottom. How do I know? Because I made up the problem and I designed it that way. So we want to know how much thermal energy was created between the child and the slide as they went down. We can still apply the same conservation of energy equations that we've been doing, where we say that our initial energy equals our final energy, but now we're just going to add our thermal energy into the mix. So the initial energy before they started going, we're going to say they started at rest at the top here. Before they started going, we just had gravitational energy. Some of that gravitational energy at the bottom here becomes kinetic energy, but not all of it. So in addition, some of it became heat or thermal energy. And we can figure out exactly how much just by looking at the difference between these two things. So we can plug in mgy, 1/2 mv squared, and thermal energy. Be careful not to cancel out mass in a situation like this, because there's no mass in this term here. You have to have a mass in all three terms to cancel it. So don't do that. That would be bad. Alright, now I'm going to just kind of come up here and start plugging in numbers. The mass was 50. Whoa, that was weird. Let me see if I can undo that. There we go. The gravity, we're assuming this is on Earth, so 9.8. And the height was 3 meters. You can set that equal to 1/2 times the mass times the velocity, which was 5 squared, plus the thermal energy. This over here, when you multiply it out, gives you 1470. So that's how many joules of energy the child had at the top of the slide. Multiply this out, and it gives you 625 joules of kinetic energy at the bottom. And the rest is thermal energy, so all you have to do is subtract, and you get 845 joules of thermal energy was created by the child going down the slide. So not too different from what we've done before. We're just adding this extra piece here. Alright, the other way we can figure out the thermal energy is what we call the work approach. So if I have, let's go back to a 20 kilogram box, because my boxes are always 20 kilograms for whatever reason. And let's say we're pushing on it this way, some push force of 100 newtons, and there's some friction, very crooked friction, acting to slow this box down, and let's say that our friction is 80 newtons. And just like in the previous ones, we're going to push the box 5 meters. And I want to know how much thermal energy was created. Well, that thermal energy is created due to friction. It's the amount of energy that friction removes. So our other description of how much energy a force removes is the work done. So the work done is going to equal the negative of the amount of thermal energy created, because thermal energy, we're going to have positive quantities, but if we're taking energy out, we want our work to come out negative, right? So this is the work done by friction. The work done by friction is just force times distance. In this case, it's friction force times the distance. That's going to equal the negative of our thermal energy. The friction force, we said, was 80. The distance was, and I'm going to make that negative because it's going in the opposite direction of motion. This quantity here, one of them has to be negative, so I'll just throw a negative out front. The distance was 5. That's going to be the negative of our thermal energy, and we want those negatives to cancel out because we want positive thermal energy. So 80 times 5 is 400 joules of thermal energy created in this situation. We didn't need to know anything about this push force as long as we knew how much friction and what distance. Now, in more complicated problems, I might go on and ask, well, how fast is this moving? In which case, you would need to know the work done by the push force and find the net work and all of those things. But we've kind of already seen that already. So here we go. Another way to find the thermal energy is going to be the friction force times the distance. Okay? And sometimes we'll combine kind of the two approaches. Let's jump back to our stick child on the slide. If we wanted to figure out what was the friction force acting on this child as they slid down, we would need, sorry about that, we would need one additional piece of information, the angle of the slide. So let's say this is a 40-degree slide. So I want to find the friction force now as that child went down. Well, if this is the amount of thermal energy created, I can set my friction force times my distance equal to the negative of that thermal energy from the equation we just saw on the last page. So I do need to know the distance over which friction was acting, and that's not the vertical distance here, it's the actual distance that we were sliding down. So the distance, you do a bit of trig, it's going to be 3 over sine of 40, because we're solving for the hypotenuse this time. So that distance works out to be 4.67 meters long, so I can plug that in here. So friction times 4.67 equals negative 845. So friction is 845 divided by 4.67, which is going to be a negative 181 newtons. At this point, you can drop the negative because I don't really care about it when it deals with forces, right? But when you're dealing with energy and when you're dealing with work, it does matter. So we can combine the two approaches in certain problems here as far as using conservation of energy, which is what we did here, and then the work approach, which is force times distance, to relate thermal energy.